Happy birthday, first of all, by the way. Okay, so what's a limit? Well, when you're asked to find the limit of a function f of x, say as x tends to a, then what it's asking you is, as x gets closer and closer to a, without actually being equal to a, and that condition, by the way, is really, really important. It's the only thing that makes this sort of non-trivial. Then what value does f of x get closer and closer to? And of course, most of the time it's going to be f of a, as you might expect. So if you look at this down here, I've made sure that this thing passes through the point 2, 3, although you can't actually see it on these axes. Obviously, as x gets closer and closer to 2, then f of x is going to get closer and closer to 3, which is exactly what you might expect. So we'll have a look at the next slide on various things that can go wrong and why, of course, that condition is so important. Okay, well, sometimes a limit doesn't exist for a function at a particular value, and here's an example of that, where you've got the limit is x tends to 0, 1 over x, and that doesn't exist because basically when x equals 0, the function is not defined. And as you can see from this graph, if you approach it from the top, as it were, you get plus infinity. If you approach it from negative values, you get minus infinity. So the value at x equals 0 doesn't actually exist at all. So the only thing you could say, for instance, is something like this down here, which is the limit as x tends to 0 upwards from negative values is going to be minus infinity, and the limit as x tends downwards to 0 is plus infinity. So you could say that, that's true, but you can't actually say that. So there's one of the things that can go wrong. Okay, well, sometimes a limit can exist, but not be equal to the value of the function. And here's an example. We've got this function f of x here, and it's equal to x everywhere except for the point x equals 2 when I've set it equal to 0.5. So you can see this point has just been sort of pulled out from there and put down there. Okay, so as x gets closer and closer to 2 without actually equaling 2, then f of x is going to get closer and closer to 2 up here without actually equaling 2, and so the limit as x tends to 2 will be of f of x will be equal to 2 because it just gets closer and closer. And that, of course, is not the same as the function because I've deliberately defined it to be different. Now, when this sort of thing happens, we say that the function is discontinuous at x equals 2. And if a function is equal to its limit at some point, and that limit is also finite, we say that the function is continuous at that point. And most functions you will encounter are continuous everywhere except perhaps at the odd point. So let's go and have a look at what can happen when you actually calculate limits. If a function is continuous at some point, then the limit at that point is just the value of the function. So what can go wrong? Well, when you're trying to calculate the value of a function, you might end up with any of the following type of expressions, and these are all called indeterminate forms, and in fact they don't have any meaning. So what it essentially means is that the function is undefined at that point. So the question is, what should you choose for the value for the function at that point? And the obvious choice is the limit as the value of x tends towards the point under consideration. So that should be your choice for the value of the function. Because you don't want a situation like we saw on the previous slide where some arbitrary value has been pulled out of position. Now, you can also look at the limit as x tends to infinity. So as x gets very, very big, you can ask what the value of the function is in that particular case. And if you do that, there are two particular approaches you could choose. you could do what I do, which is the sort of rough and ready way of doing it, which is if you see various powers of x added together, just throw away all of them except the highest power. So in this particular case, you've got 2x there minus 1, so that minus 1 is going to be negligible, so you can just throw it away. And you've got x squared, and that's going to dominate everything. So the plus 10x plus 1 is going to be negligible in comparison when x gets big, so you can just throw that lot away and you get that. And you can now just simplify the expression. And it's just take the square root of that lot and cancel the x's out, and you get a half. Okay, now the second way, which is really a bit more rigorous, it's really the right way of doing it, is to rewrite everything in terms of 1 over x and let 1 over x go to 0, because if x goes to infinity, then 1 over x will go to 0. And if we do that here, if we divide the bottom by x and the top by x, well, you're going to get 2 minus 1 over x for that. And if you divide the top by x, you'll have to divide inside by the square of x, because inside that square root. So you'll get 1 plus 10 over x plus 1 over x squared. And if 1 over x goes to 0, then 1 over x squared, which is just the square of it, is going to go to 0 even faster. And so that lot's negligible, and that lot is negligible, and you just get basically 1 over 2, or a half. So the case when x goes to infinity usually is quite simple, in fact, because although you get a lot of infinities everywhere, they just simplify usually most of the time, because you just got to throw most stuff away. Okay, here's a more interesting case. This time we're looking at the limit is x equals 2. So because we're not going to infinity, we can't throw stuff away like we did when x went to infinity, and we got no sort of 1 over x tricks, because it's not applicable now because x is going to 2. Right, well, the first thing you do is substitute x equals 2 into that and see if it works, because you never know, it might do. But if you do that, you get 0 over 0. So what does that mean? It means that if you look at the bottom here, it is when you substituted, you got 0, so that means you found one of the roots of that quadratic. And if you've done that, it means you can factorize it out. And if you do that, you find x equal 2 is one of the roots, and minus 3 is the other one, and that thing, of course, factorizes like that. So that then cancels with that x minus 2 there, and now if you substitute x equals 2, you get 1/5. So that's the limit. Now there's another way of doing this, thanks to some French aristocrat called the Marquis de l'Hôpital. And there's a rule that he's got for calculating indeterminate forms. And that's what we'll do next. Right, L'Hôpital wrote the world's first textbook on differential calculus, and in it he wrote the following rule. If you've got two functions f of x and g of x, and you're looking at the ratio of f of x over g of x, and you're looking at the limit as x tends to a, then if that's 0 over 0, or infinity over infinity, or plus infinity over minus infinity, or something like that, then what you can do is just differentiate each of those functions and look at that limit instead. And if it exists, then that's the right value. So let's have a look at that in action. Here we're looking at the limit as x tends to 2 like we did in the previous case. And what you have to do is just differentiate the top. Well, that's easy, that's just 1. Differentiate the bottom, that's 2x plus 1. And then look at that limit as x tends to 2, and it's a fifth. And so that's the answer, because it's got a limit and it's a fifth, so that's the answer to that limit. Now, also note in the above that a here could be in, plus or minus infinity. It's quite general. But the rule only works if the limit exists. So Let's have a look at a case where the limit doesn't exist. Here we've got limit as x tends to infinity of x plus sin x over x. And if you look at that, if you divide by x here, it's 1 plus sin x over x. And sin x is always going to be between plus 1 and minus 1. So if you're dividing by x, x is going to infinity. So that term is going to get smaller and smaller and smaller as x gets bigger, and so it will become negligible and vanish eventually. So the limit as x tends to infinity is going to be 1. Now if you differentiate the top here, you get 1 plus cos x. Differentiate the bottom, you get 1. And if you look at this, as x tends to infinity, there is no limit here, because cos x of course just goes between plus 1 and minus 1, so when you add 1 on, it will just go between plus 2 and 0, and it of course doesn't have a limit. But this rule works in an awful lot of cases, so it's useful to do.